All right, guys. Am I audible? Give me a thumbs up if I'm audible. Okay. So I'll just start off. I'll let people in when they do come in. Uh, Wait, give me some time. Okay. I hope the screen is visible. Fair enough. Look, last class, which was on Thursday, we were talking about temperature. We looked at different types of thermometers, right? And we covered some amount of temperature scale. We talked about what the Kelvin scale is in general, and we talked about triple point, and then we started having a conversation about how the energy changes with different states. So when we have solid to liquid, liquid to gas, how the energy changes, let's say for potential energy and for kinetic energy. When we have no state change, we only have temperature increasing, we have a difference in kinetic energy. And when we have a state change, there's no change in kinetic energy, and the only change that exists is of potential energy. Fair enough. So we talked about that. We talked about how intermolecular forces vary, kinetic energy varies, potential energy varies. Then we went into a conversation of the state diagram, how melting happens, how boiling happens, and how long it takes for each of the type of state changes. So when you have this B2C region, and in this case, we have what happening? Melting. And in case of melting happening, some amount of, what do you call it? Intermolecular forces are broken. Some amount of bonding is broken. Okay. Not entirely, because liquid still occupies a set amount of volume. And then you have the D2E area, this one. What happens here? Evaporation takes place, boiling takes place. All of the bonds are broken. And when this conversation of all bonds being broken takes place, we need a lot more energy. Because right now, we're going to a state of a zero potential energy, right? Gases, we assume for ideal gases, they have zero potential energy. And for gases to be that far apart, for the bonds to be broken, all the bonds to be broken, we need way more energy over here. So the del T that you see on the x-axis is way more. Why again? Because all bonds are being broken. And why is the del T over here B2C less? That is of melting, because some amount of bonds are being broken, not entirely. This is the difference. This is the only difference between melting and vaporization. All right, fair enough. So now there is one thing that I want to discuss again, that is of last class, and that is I was explaining to you guys how thermocouples work. Okay, and while explaining this, I did show you guys a diagram. And the thing is, later on, I thought that diagram is not really as suitable, let's say. Okay. And I felt that I should show you guys a better, um, a bit more, something that I can explain a bit more in details. So I went on and found out this specific diagram of a thermocouple, which is a bit more exact, I would say. This is the type of thermocouple diagram you can see. There are other forms. The one I showed last class, those were two types of other thermocouples you can see in exam papers, in books, different types basically. But today I want to explain this one. Again, revisit the thermocouple one because this is a different diagram I have. The explanation I had last class, that whenever there is a difference in temperature between two points, electrons flow from a region of high energy to a region of low energy. Keep that in mind. So whenever there's a difference in temperature, electrons start flowing, right? And that electron flow, right? Due to that electron flow, due to that distribution of charge, one place with less charge, one place with more charge, we have an EMF. That's how temperature and potential difference is related. So as the temperature increases or the difference in temperature increases, my EMF increases. That's the core idea and that we discussed last class, right? So there's nothing wrong with that, but I just want to show you this diagram. And I want to get into a bit more details, although it may not be required in your syllabus. Still, let's visit this. So what do we have over here? Take this as a typical voltmeter, galvanometer, whatever you want to call it. But this basically gives you the voltage reading or the potential difference reading, right? So I have a voltmeter over here. That's good. Now I have a circuit over here. So this voltmeter is connected to a junction. We call this a cold junction. And you know what the temperature of this is? Could be anything, but the main idea is the temperature is known. So let's say I'm telling you guys the temperature of the cold junction, this entire bar, this entire metal bar. I know the temperature to be, let's say, 0 degrees Celsius. That's fair. Now, what I have on the other side over here is two separate wire. One is made out of metal X, let's call it iron. The other is made out of metal Y, let's call it copper. And this junction over here is the point I put in different places to measure the temperature. So let's say I put this junction in a beaker filled with water, right? And I want to measure the temperature of this beaker filled with water. Okay? Now, why is it that we see a potential difference over here? So let's take an example. I put this in a beaker filled with, let's say, way more than 0 degrees Celsius, 40 degrees Celsius. Fair enough. Now, you know what happens? Electrons from over here, right? Electrons from over here start traveling to the cold junction. Why does that happen? Because there's more energy over here at the hot junction compared to the cold junction. The cold junction has very little energy. So what you see when you heat up a metal bar, right? You have a metal bar and you provide heat over here. What you will see is electrons start flowing to the colder end. This is something you guys know. You have heard of conduction. Conduction happens because of two regions, right? One is vibration of atoms, the other is flow of electrons. Okay? So this electron, due to heat over here, due to having high energy, starts flowing to the colder end. Right? That's what happens. Same thing happens over here. I heat this area up, let's say 40 degrees Celsius. Electrons start flowing from this warm region of high energy to the cold junction, which is 0 degrees Celsius. Okay? Now, notice one thing. Electrons go over here. Electrons from here to here go over here. Why is it that the voltmeter, which is connected about this point and about this point, gets a potential difference? Why? Why is it that we see a potential difference between these 2 points? Electrons are flowing on both wires, through both wires, to the cold junction because of a simple logic. From warm region to a colder region, electrons want to flow. So why is it that when I connect one part of the voltmeter over here and one wire of the voltmeter here, I see a potential difference? The key part over here is a difference in wire, difference in type of wire. What would happen if iron is metal X and metal Y is also iron? What would happen in that case? You would see zero potential difference, 0 volt, zero PD. You know why? Because the rate of electron flow from this hot junction in iron would be the same as rate of electron flow from this wire as well, because both are the same material. The key part is, which I've explained over here extensively, whenever you have the same type of material, they carry same thermal properties. So if I have iron and iron over here, they transfer electrons due to heat at the same rate. At the same rate. So if I have iron in both wires and I warm this region up, right? I heat this region up, electrons flow through the wires, both wires the same rate and same accumulation of electrons take place at both these points. So if 40 electrons go from here to here, 40 electrons also go from here to here because of the same type of material. You have to understand that, right? Due to same type of material, the same amount of electrons flow. And hence, when I have the same amount of electrons at both these junctions, I see no potential difference. Does the length of the wire matter? Yes, it can matter because it will hinder the amount of electrons that get to the point. That is possible. But it is not seen as that much of a difference because then we would simply increase one portion of the wire. So if I have iron over here, sure, within some, if a fixed amount of time I take, and this is 2x the wire 2 is 2x the length of the other wire, both are iron. Yes, if I observe between a fixed amount of time towards the beginning, sure, I will see that the amount of charge accumulation is less, but eventually with time, as all the electrons flow out, the charge accumulation will even out to an extent. Okay, so nope, I am simply trying to because most people, when teaching this part, get confused about how thermocouples work. That is why I'm explaining. You don't need to understand in details how thermocouples work in your CIE physics syllabus. Okay, I'm just giving a bit of extra info over here because I have had this question come in a bit more than usual. Okay, that's the only reason I'm explaining. You don't need to know extensively. Now, the thing is, over here, what's happening is, so if I just omit the length part, now, what happens if I change iron to copper? Copper and iron has different thermal properties. Different what? Thermal properties. So they, even though they're heated till the same temperature over here, 40 degrees Celsius, electrons will flow through both wires at a different rate. At a what? Different rate. So if 40 electrons go over here, probably 35 electrons go over here. So do you see there's a difference in charge accumulation across these 2 points? Yes, you do. And hence, due to a difference in charge accumulation, you have a potential difference. You have a potential difference. This is where the potential difference comes in. That is why you need different types of wire for a thermocouple to function. Now, what happens if I increase the 40 degrees to, let's say, any random example, 50 degrees Celsius? They still have a difference in rate of flow of electrons based on metal X and metal Y, and different rate of electrons flow through both wire, but due to now an increased temperature at the hot junction, more electrons flow through both X, through Y as well. And the difference in charge accumulation also increases. Also increases. The more you increase the temperature, what happens is the difference in charge accumulation keeps increasing. Do we get that? So as you increase the temperature, due to the wires having different thermal properties, different rate of flow of electron, and as you change the temperature, increase the temperature, what happens? The difference in charge accumulation also increases. So the first idea you need to understand is having different metal wire is important. Why? They have different thermal properties, hence rate of flow of electron is different. B, what you need to understand, as temperature increases at the hot junction, while the rate of flow of electron, both in X and Y will increase, but the charge accumulation difference will also increase. Okay? The charge accumulation difference will also increase as you increase the temperature. And it wouldn't have happened, there would be no charge accumulation difference if both were the same wire. That's the key idea I wanted to put across. And the last thing I want to clarify is last class I mentioned that EMF will increase as I increase the temperature at the hot junction. That is correct. EMF will indeed increase, but the gradient of increase, that is, will the EMF increase with increasing rate or decreasing rate? So in both white and yellow line, what you see is, in both cases, EMF is increasing, but one with a decreasing gradient, the other with an increasing gradient. Now, what you will typically see and what I have typically seen is the yellow line. That is what I have seen. That's why in first class I showed you the yellow line. But later I thought about it that if I have different metal wire pairs, can it be that there's a decreasing gradient EMF increase? And turns out, yes, depending on different metal wire, you can have an EMF to temperature graph looking like the white line with decreasing gradient. But that distinction is not important for you. What you need to understand is EMF and temperature has a non-linear relation. This is what you guys need to understand. So as EMF increases, temperature also increases, or vice versa. As temperature increases, EMF also increases. And that happens in a non-linear manner. So it's not a straight line. It's not a proportional, right? It's not in proportion. It's not in linear proportion. It's in non-linear proportion. It can be with increasing gradient. It can be with decreasing gradient. Both are possible. That's the second thing I wanted to clarify. One was the label diagram. I wanted to show you guys a different one. B, the graph, there can be a difference in the graph. These two things. Okay, these are the additional info from last class. Now, if we move on to the new topic, not exactly new topic, extension of what we were discussing last class, I told you guys that during the melting process, less time is required. Why? All bonds are not being broken. And during the evaporation process, all bonds are being broken, hence more time is required. That's the key idea that I want to flag post today's. Once you understand that, and you understand this entire conversation, that where kinetic energy increases and where potential energy increases, you're good to go. Okay? So where does kinetic energy increase? Only when temperature increase. So A to B and C to D and E to F. Keep that in mind. This is a question that may come your way. I'm again saying this. Okay? When temperature increases, kinetic energy increases. And when state changes, B to C and D to E, potential energy changes. Does kinetic energy change between state change? No. Why? Because temperature remains constant. Look at the graph. Temperature remains constant during state change, hence no change in kinetic energy. Okay? If you understand that, brilliant. Then you can answer half the questions. Now, you to an extent from IGCSE and also most likely AS know what specific latent heat of vaporization is and specific latent heat of fusion is. Which one is which? Specific latent heat of vaporization is when I evaporate or boil liquid. Okay, so that is the specific heat of vaporization. Basically, the amount of energy needed to boil or evaporate 1 kg of liquid. Okay, okay, that's what latent heat of vaporization is. How much energy do I need? How much energy do I need to convert 1 kg of liquid to a gas? Fair? That's the conversation. Same with latent heat of fusion. It's just that you don't boil or evaporate, you melt. So how much energy it takes to melt 1 kg of solid to liquid? Okay. Now for solid to liquid, notice over here, what is how much energy do I need to, let's say, convert 2 kg of I don't know, copper into liquid? So I would say the energy required to convert 2 kg of copper to liquid would indeed be, is it lacking? Okay, so 2 kg of copper would be 2 times whatever the specific latent heat of fusion of copper is. So let's say it is 100 joules. Okay, 100 joules is the energy needed to convert 1 kg of copper into liquid. So I multiply 2, which is the mass, times specific latent heat of fusion. Do we get the idea? Great. So this is solid to liquid. What happens liquid to gas? Same thing again. But L basically defines specific latent heat of vaporization. How much energy is needed to convert 1 kg of liquid to gas? Fair? We understand that? Okay, it's the same thing. This is something you guys have visited again and again in the past. If you have forgotten, revisit this. So this is the formula. In both cases, L basically defines different things in different scenarios. When melting, it is fusion. When vaporizing, it is latent heat of vaporization. Granted, you understand that. The next thing I want to have a conversation about is the cooling effect due to vaporization. Okay, today we're going to get into some very complicated things, some very conceptual things in the ideal gas section. But yeah, what's the time? Okay, fair. So look, I have water over here. Okay. Now, what happens in let's say any cup of liquid, any bucket of liquid, any amount of liquid that you have. Now, at the top position, whatever liquid you have, they tend to have more energy. They tend to have more energy. They roam around in the liquid. They glide around the liquid with higher kinetic energy. So the liquid around the surface, what happens is they tend to have high kinetic energy or higher amount of energy. That also means they have high velocity. Okay. So liquid around the surface tend to have higher energy. Think about it logically. Try to bring in your physics intuition. When you have a puddle of water, right? When you have a puddle of water by the road, what happens? The water from the surface start evaporating, and then water from the depth of the hole, pothole, starts evaporating as well. So the surface water evaporates first. Why? Because they gain the energy fastest, because sunlight is hitting, there's wind coming in, everything. So they come in contact or absorb the energy first. So when molecules have high amount of kinetic energy compared to the liquid below, they tend to evaporate even before the boiling point. If I'm having a conversation about, let's say, water over here, which has a boiling point of 100 degrees Celsius, right? Even if my liquid throughout this bucket of water has not reached 100 degrees of Celsius, even then, water from the surface can evaporate. Is that clear? Why can that happen? Because probably they have higher amount of energy compared to liquid at the bottom, because they're gaining the sunlight, they have wind coming in, and they get that enough kinetic energy, hence high velocity, so they can escape the surface tension. They can break their bonds inside the liquid, that is intermolecular forces, and also escape the surface tension. And they emit as gas. Why? Again, because they have enough kinetic energy. Now, what happens when this happens though? What happens? When evaporation takes place before boiling point, and I have my high kinetic energy, high velocity molecules escaping my bucket of water, the average kinetic energy of the bucket decreases. What that means is when I have, let's say, high Ke molecules at the surface, low Ke molecules at the bottom of the bucket, what happens? The average, let's say, the average of all the kinetic energy of all the molecule is, let's say, normal. I'm just saying it arbitrarily. Let's just call the average kinetic energy of the molecules normal. Now, when all the high kinetic energy molecules evaporate into gas, I'm only left with low kinetic energy molecules because all the gases have evaporated. I mean, all the high kinetic energy molecules have evaporated. So I'm left with low kinetic energy. So my average kinetic energy of the molecules have decreased. So now the average kinetic energy of the bucket of water is less low. Why? Because the high kinetic energy ones have evaporated. Fair enough. What happens when the Ke of your molecules decrease? Temperature decreases. Why? Temperature is a measure of Ke. If your kinetic energy of the bucket of water has decreased, temperature has also decreased, my friend. Temperature has also decreased. This is why when your sweat evaporates from your skin, you feel colder. There's a cooling effect on your hand, on your face, on your hair. That's why you feel cooler when evaporation takes place. Because all the high energy, high temperature molecules have evaporated, you're left with low energy sweat molecules or water molecules on your skin, and that gives you a cooling effect. That decreases the temperature on your skin. Do we get the idea? Yes? Fair enough? Okay. Give me a moment. So the average kinetic energy is decreasing, hence the temperature of the bucket of water also decreases. So this is the conversation at the end of the day. This is the cooling effect. We understand this, we can move on. Okay. Any question, do let me know. Slido is open. I just opened it. I forgot about it. Anyways, you can ask me on Slido or over here. No problem. Fair. Okay. Now, heat capacity. I mean, this is something you guys have learned extensively previously, but I'll still go over this. What is it? Specific heat capacity, or denoted as C in equation, is basically the amount of thermal energy required to raise temperature of 1 kg of any substance by 1 degree Celsius. When state change happens, is there any specific heat capacity involved? So if my thing goes from solid to liquid, is there any specific heat capacity involved? No, because temperature does not change. What does it say? When the temperature increases by 1 degree Celsius for 1 kg of substance, what's the energy needed? That is specific heat capacity. Your temperature needs to increase. So in state conversion, there is no specific heat capacity involved. Be clear on that. Okay, be clear on that. Okay, fair enough. So now, what is the formula for let's say yes, you can. Yeah, that's an accurate description. I mean, if you just add in thermal energy in the definition, just add the thermal part, more accurate. Okay. Often, what you will see with my notes over here, I tend to highlight certain important things with yellow. So I probably the heading is yellow, and also certain important parts I just highlight with yellow. So that's an indication of what may be an important word or keyword. Okay, fair enough. Look, you can also check with the MS if you want to clarify. Anyways, coming back to my definition of energy provided to any substance. How do I find the energy that is provided to a substance that has, let's say, that has mass of 2 kg, increases its temperature by, let's say, 2 degrees Celsius, and I know its specific heat capacity to be 4.12 joules. How do I know how much energy was provided to this liquid to increase its temperature by 2 degrees Celsius? How do I know that? We use a equation. What is the equation? The equation tells me del Q, or change in energy or del E. Different people say different things. You will see del Q of it in the question paper. It's basically the change in energy. Can be written as mass. So how much of the substance I am increasing the temperature of, the specific heat capacity of that liquid or solid, whatever it may be, or gas, could be anything, no problem, could be any state, no problem. What is the specific heat capacity of that substance? So how much energy I need to convert or increase the temperature of that 1 kg of substance to 1 degree Celsius, right? I want the increase to be 1 degree Celsius of a 1 kg substance. And what is that energy required? That is specific heat capacity. Okay, so that's C. And what is the del theta? You will see del T, you will see del theta, different symbols, don't get confused. So that del theta is the increase in temperature of the entire liquid. What is the increasing temperature of the entire liquid? I am telling you guys 2 degrees Celsius or 2 Kelvin. So don't get confused over here. Over here, you can, the difference in temperature, you can use change in Kelvin, change in Celsius, no problem. The reason I say that though is there's a linear relation between Kelvin and Celsius. What does that mean? If 0 Kelvin is minus 273.15 Celsius, then 273.15 Kelvin is simply 0 degrees Celsius. They're linearly related. If I increase Kelvin by 1, if I increase Kelvin by 1, Celsius also increases by 1. It's a linear relation between the two. Keep that in mind. So if I tell you that the temperature change of the liquid goes from 273 plus 25, 298, okay, 298.15 Kelvin to, let's say, whatever 5 adding would do. So 303.15 Kelvin. Okay. So I'm telling you guys, this is the temperature difference in Kelvin, and the temperature difference in Celsius would be 25 degrees Celsius to 30 degrees Celsius. In both cases, it's the same thing, guys. It's the same thing in both cases. Keep that in mind. It is the same thing. 298.15 Kelvin is the same as 25 degrees Celsius. 303.1, if my calculations are all right. If it's wrong, do let me know. But yeah, 303.15 Kelvin is the same as 30 degrees Celsius. Okay? And you will often see 25 degrees Celsius in your question paper because this is the room temperature. Okay? This take considered as the average room temperature across the world. Not across the world. Just you're doing UK syllabus. So I guess in UK they consider 25 degrees Celsius to be the ATP. Sorry, room temperature. Anyways, point is it's the same thing. So what is the difference in Kelvin over here? 5 Kelvin. Agreed? And what is the difference in Celsius? 5 Celsius, 5 degrees Celsius. It's the same thing. So when you're working with difference in temperature, Kelvin and Celsius can be used interchangeably. Difference, keep that in mind. Difference. So when you're working with difference in temperature, it's okay to calculate with Kelvin or degree Celsius. When you're doing this equation, PV is equals to nRT, and you have to include this temperature, do not include Celsius over here. This is not difference in temperature. This is the temperature itself. What is the temperature of the liquid? This is what it's saying. What is del theta? Del theta is the increase in temperature. That's the difference in temperature. Del theta is not the temperature of the liquid. Del theta is how much the temperature increased, change. What is T over here? T over there in PV is equal to nRT is a thermodynamic temperature. You have to talk about the Kelvin scale temperature. You include Celsius over here, you get an atrocious answer. That's wrong. You can't use Celsius scale. Okay? And often, again, keep this in mind, very important what I'm going to say. When they ask you to define T in PV is equals to nRT, always write T in the PV is equals to nRT equation means the thermodynamic temperature, not just temperature. You will lose marks. Thermodynamic temperature. You can't just write T is the temperature. I don't know if they still cut marks, they used to. Okay? When the question asks you, what does the symbol T mean in the PV is equals to or the ideal gas equation, you should say T is the thermodynamic temperature. Keep that in mind. Be clear on that. Why is it important? Temperature can be defined with Celsius, with the Fahrenheit scale, or the Kelvin scale. You have to make sure you specify it's a thermodynamic temperature or the Kelvin scale temperature. Okay? Keep that in mind. What's the time? Okay, fair enough. So if that is clear, let me go back to my thingy. So over here, you understand the change in temperature can be calculated with respect to Kelvin scale or Celsius scale. Okay, granted you understand that. I'll move on. So that's why I use Celsius over here. It's not inaccurate to do that. Otherwise, you guys could be confused. Why am I using Celsius even though I'm supposed to work with Kelvin? Nonetheless, how do I write down what amount of energy has been provided over here? How do I write it? My del Q, or change in energy, or the
Sir,
provided energy, is simply mass of the whatever substance I have, that is 2 kg. SI units, guys, not grams. Convert grams into kg. So 2 kg times specific heat capacity. I'm telling you guys it's 4.12. 4.12 joules per kg per Celsius is the, what do you call it? Specific heat capacity of water. Okay. You guys can remember that. It's good to remember it. Anyways, so the del theta,
sir,
yeah,
uh, I wanted to ask,
yeah, go ahead. Am I lagging or are you lagging?
is it like that?
I couldn't hear you, sorry.
Is would by thermodynamic temperature, do we mean the Kelvin scale or?
Yes, yes, yes. Whenever you say thermodynamic temperature, it automatically means the Kelvin scale temperature.
All right.
That's why the distinction. That's why it's important. Because in the PV is equals to nRT equation, if you write down, let's say 25 degrees Celsius instead of 298 Kelvin, your answer will be wrong. You need to include 298 Kelvin in the equation, not 25 degrees Celsius. That's going to give you the ultimately wrong answer. So yes. Now coming back to this, my change in temperature over here is simply 2. Call it 2 Kelvin, call it 2 Celsius, doesn't matter because difference is the same, right? Difference in temperature is the same across the scales because they're linearly related. You can't do the same with Fahrenheit, and you also won't see Fahrenheit in your paper. That's an atrocious way of describing temperature. It's very weird. Fahrenheit doesn't have a linear relation with Kelvin or Celsius. It has a very specific equation for it. You guys may have studied it when you were very young, but it is completely different. It doesn't have a linear relation with Kelvin scale or Celsius scale. So you will also not see that in your paper because there's a different formula to convert Fahrenheit to Celsius, which I forgot, but it's also not important. Okay, now what's the answer over here? It's simply 2 times 2. Whatever the answer is over here, you get it, put it in your calculator, you'll get the answer. So this is the amount of energy provided to the liquid to gain 2 degrees Celsius. Is that clear? Okay. So this is the amount of energy provided for the liquid to gain 2 degrees Celsius of temperature. And specific heat capacity unit, how do you find out the unit? Just make C the subject. So del Q divided by M and del theta. What is the unit of del Q? Joule. What is the unit of mass? Kg. What is the unit of theta over here? Basically change in temperature, Kelvin or Celsius. Doesn't matter over here. So C is going to be given by joule per kg per Celsius. Do we see the same thing written over here? Yes, we do. Did we find out how the SI unit came out to be? Or I mean, how the unit came out to be for heat capacity, specific heat capacity? Yes, we did. How? By making specific heat capacity the subject and by writing down the units. That is how the unit is found out. Okay, you guys have done this in AS where you guys had to find out units. First topic, physical quantities. What did I erase? Okay. Now, uh, what is the feature of Celsius in general? Do you know? I mean, hopefully you do. Whenever you have specific heat capacity that is very, very, very low, temperature rapidly increases. Do we understand why? Because E is equals to MCAT. I often write it as MCAT, so I'm just used to this. Whenever you have, let's say, 20 joule of energy, randomly, I'm taking 20 joule of energy provided. If your specific heat capacity is low, less, your temperature increases more because less energy is required to increase the temperature. Is that clear? Now, if you provide the same 20 joule of energy to something that has a high, I'm keeping the mass constant, let's say 1 kg of mass, 1 kg of mass. So specific heat capacity is way more. Then the change in temperature will be low. Is that clear? Is that clear? Why does that happen? Because when your specific heat capacity is way more energy is required to increase the same amount of temperature. So, low specific heat capacity means the object heats up really fast. High specific heat capacity object heats up very slow, needs way more energy to increase the temperature by the same amount. Okay? Use the equation, play around with the equation, and see how it really works. Now, often a type of question, I'm going to orally describe the type of question. You will come across this type of question very frequently whenever working with thermal physics. Let's say, typical question, I have a kettle of water. Okay, I have a kettle of water or a glass of water on a boiler plate. I don't know. And the power rating of the kettle is probably given, saying it has it is rated as 40 watts, right? So it provides 40 joule of energy per unit time. You guys know how power works, right? Power is simply work done by time. I hope you remember this part. Now, they will probably give this and they will also tell you, okay, I have liquid inside or water inside, which has a specific heat capacity of 4.12, and the mass of water inside is 1 kg or 2 kg. And find out the increase in temperature. If the basically kettle was on for, let's say, 10 seconds. Okay, so time for boiling the water, let's say, is 10 seconds. How much is the del theta or the change in temperature? Can you guys find this out? Can you guys find this out? You know what, let's check. What are you supposed to do? Go to my dear Slido. Okay, do you guys know the code? Please do know. Let's just quickly give me the answer. The code is hash 2321508. Okay, give me the answer. What is the change in temperature? What is the change in temperature? Give me the answer. Answer below. Over here, you type in your answer. For people who don't know, simply go to Slido. People who do know, start answering fast. Start answering. So you will put in this code 2321508. Okay. Why did I put in JO? Okay.
So we have to find what again? So
The increase in temperature. By what amount did the temperature of the liquid increase? So you will put it in the poll section, answer below. Okay.
Can you show
So
the
I'm telling
question?
you guys, sorry.
Can you show the yes? Thank you.
Yeah. So you guys know the equation. E is equals to MCAT, right? So specific heat capacity, I'm telling you guys, of liquid is 4.12. Mass of the liquid is 2 kg. The power rating of the kettle is what? 40 watts. How long was the kettle on? Time 10 second. Granted, all of these information is provided to you. What is the del theta or increase in temperature? What is the increase in temperature? This is what I want to know from you guys. Okay. I just want to know the increase or the change in temperature. How do you find the total energy? Remember this equation. Okay, I have two answers. Two more. I'll discuss fast. It's simply putting into the calculator, you know, the equation, simply put in the calculator, the values. This is the more straightforward question you'll get. Okay. Okay. I'll go ahead and the answers I have right now, yeah, they're accurate. Fair enough. So look, it's simple. It's very simple in nature. It's simply telling you that the power rating is given, and power can be expressed as work done per unit time. So if the power rating is 40 watts, that means 40 joule of energy is transferred per second. To what? To this liquid. Is that clear? Now, what is the total work done by the boiler plate? Not the boiler plate, the kettle. 40 times how long it was on for? 100. That is 400 joules of energy supplied. Okay, so I can say 400 joules of energy has been supplied to my liquid. And what is the expression for increase in temperature equation? MCAT. This is how I write. You can write it as delta as well. Doesn't matter. What is the mass of liquid, my friend? 2 kg. Is that clear? What is the specific heat capacity of water or the liquid I have? 4.12. What is the change in temperature? That is what I find out. Can you make del T the subject? Yes, you can. And when you do that, this is expression. So I'll simply write it as, can you simply put this in the calculator? This expression, and will you find out the answer? You know what? I'll even do that for you. Okay, 400 divided by 2 times 4.12. Whoa, yes. So the answer is del T is 48.54. What does this mean? The temperature increased of the liquid by 48.54 Kelvin or Celsius. So the increase in temperature over here was 48.54 Kelvin or Celsius. Is that clear? This is the increase in temperature. This is the increase in temperature. Any question about this? Yes, no? Any question about this? Simple maths. Okay. If you do, welcome to ask. No, I don't see any question. Okay. Now, latent heat capacity. I've explained this. Amount of energy needed to change the state of 1 kg of specific. Sorry. Latent heat. If I just write down latent heat capacity, that just means any amount, any mass of liquid, how much energy I need to raise the temp. Sorry, convert the state. So if I have, let's say, 2 kg of liquid, let's say water, and I ask you what is the latent heat capacity, you will tell me 2 times whatever the latent heat capacity is. I don't really know. Let's say 40. So you'll tell me the latent heat capacity of this 2 kg liquid is 80 joules. But specific latent heat capacity means not 2 kg. What would be the energy needed to change the state of 1 kg of water. That's why specific, the word specific latent heat capacity is important. Whenever you add the specific word, that means 1 kg of a substance. If the specific is dropped off, that means whatever the amount of energy, whatever the mass is, it's all right. You can simply provide, calculate and say, okay, if it's 2 kg of mass, the energy required to change the state would be 80 joules of energy. That would be the latent heat capacity of the substance. And if it's specific, you need to talk about 1 kg of that mass. Okay, is that clear? That's a distinction. So it's always better to write down specific. So we understand all of this specific heat, specific latent heat of fusion and vaporization. We discussed this. Granted, that is clear. This is, of course, the equation which you guys saw. E is equals to ml or E is equals to lm. Doesn't matter. The last thing I want to show you guys in the temperature chapter is this brilliant question. Not brilliant, it's a decent. But anyway, I wouldn't be surprised if a few people would get stuck on this, especially if you're doing it for the first time. Do we remember last class when I was talking about the mercury thermometer? I asked you guys a question. What did I ask you guys? That when I put in the thermometer into a beaker filled with liquid, as the mercury gains energy to increase its temperature to whatever the temperature of the beaker full of liquid is, will the beaker of liquid lose the temperature? So what I told you guys or asked you guys was, I have a beaker filled with water. I'll just put it in white. I have a beaker filled with water. Temperature of this is 40 degrees Celsius. And I put in a thermometer, my friend. And this has mercury. And when is the reading complete? The reading is only complete when the temperature of the bulb of the thermometer, so T of this, and the temperature of the liquid is same. That is when we take the reading, when the temperature on the mercury thermometer stops increasing. Whenever there's a thermal equilibrium, that is to say, temperature of the bulb or of the mercury, temp of mercury is equal to temp of liquid or whatever substance you're measuring. That is when we take the measurement. That is when we take the temperature reading. Okay. Now, what I asked you guys last class is, as the bulb over here, or as the mercury over here gains temperature or gains energy from the beaker of water, does the water lose energy enough to decrease its temperature to, let's say, 39 degrees Celsius so that it can compensate for the mercury gaining the energy? And your answer was, whoever answered last class was pretty much accurate, that the energy transferred to the mercury is so little that the temperature of the liquid doesn't really change. So if you look at this equation, MCAT, when your specific heat capacity of the liquid is so high and the mass of the liquid is so high, even if you provide 20 joules of energy to the mercury, the temperature doesn't really decrease that much. It does not decrease that much. Because you just need to lose so much energy as a liquid to lose the temperature. The 20 joule of energy being provided, my God, that 20 joule of energy provided to the mercury doesn't really matter. While for the mercury, it matters. Why does it matter for the mercury? Because the specific heat capacity of mercury is what? What did I tell you guys last class? Is very little. It barely needs 20 joule of energy to increase the temperature by 1 degree Celsius. The specific heat capacity is just so small for mercury, it doesn't need that much energy to increase its temperature. And whenever the temperature is equal for the mercury and the liquid, thermal equilibrium. And hence you take the reading. But this is where the question comes in. it is not wrong that energy is lost by the liquid to increase the temperature of the mercury. So in this question, what we will discuss is how much in reality does the beaker filled with water really lose temperature? We always assume that it's very little, so it's negligible. But using this question, what we will find out is, does the beaker of water lose enough temperature to compensate for the energy provided to the mercury? Okay, so notice one thing. I'll read out the question for you guys. There's a thermometer over here, initially at 23 degrees Celsius, which is the room temperature. I mean, they're giving it as the room temperature. And it is used to measure the temperature of an insulated beaker of water. That is at 37.4 degrees Celsius. So I'm putting this thermometer into a beaker filled with water. With what temperature, guys? 37.4 degrees Celsius. And my thermometer over here has how much temperature? What is the temperature of the mercury in thermometer? It's going to be simply 23, 23 degrees Celsius. Is that clear? So do you see a disparity between the temperature of the mercury and the water inside? Yes, you do. So where will heat flow from? From the beaker to the mercury. That much we all understand. We're clear on that. So who loses energy over here? The beaker filled with water. And who gains the energy? The mercury. This we all know. Fair enough. Let's move on with that idea. Now, they're telling you the bulb of the thermometer is inserted into the water and the water is stirred until the reading on the thermometer becomes steady. What did I tell you guys last class? When do we take the reading? When the temperature on the mercury thermometer stops increasing. Whenever we see that the rise in temperature stops, we take the reading. This is what they've mentioned over here. Clear? Great. Great. Now they have given you some important information to do the maths. They have told you that the mass of water in the beaker is 18.7 grams. What is the mass of water inside in the beaker? Keep this in mind. What is the mass of mercury in the thermometer? That is, how much mercury do I have inside the bulb or throughout the thermometer? This entire mass of mercury, what is that? They've given you as 6.94 gram. And the first thing I want to notice over here, isn't the mass of liquid and mercury very similar? Yes. Whenever you want to take the measurement of something, some scripts, some papers may say that the amount of liquid that you're working with should be a lot. The mass of the liquid should be a lot so that the energy loss for the liquid is negligible and hence the liquid's temperature shouldn't change as much. Over here, what I see is the mass of the liquid is very similar to the mass of mercury. Now, in general, it's always better that your liquid has a higher mass or more quantity. Is that clear? It's always better. Why? Because then the temperature change of the liquid is negligible. Okay? But so I look at this, and my first instinct is okay, there probably will be a distinct and identifiable change in temperature for the liquid. Let's look. Let's see with maths what the amount of difference is, right? So, what is the specific heat capacity of the water? The C of the water is 4.18. Okay, they've given this to you guys. By the way, one more thing, always look at the units. Sometimes what they do is, wait, okay. Sometimes what they do, what did I write over here? Joule per kg. Okay, so yeah, that's what I wanted to mention. Sometimes they write this as 4.18 or, well, 4180 joule per kg per Kelvin. Do you see the difference between these two? So sometimes the specific heat capacity can be given in terms of kg. This is a very typical difference in question. You need to be very keen on this. You need to see what the unit over here is. Now, when you're working with joule per kg per Kelvin, which I would say is the accurate unit because kg is the SI unit, then the mass of the liquid should be in kg in your calculation. So when you're doing MCAT, the reason I'm saying this is common mistakes happen over here. Okay, so I just don't want you guys to make these mistakes. The mass over here, if you're taking as joule per kg per Kelvin, then your mass should also be in kg. Make sure the units are same. If your mass is in kg, then it's okay to write your specific heat capacity in terms of joule per kg per Kelvin. So notice for 1 kg, you need 4180 joules. For 1 gram, it is 1000 that. So 4.18 joules. Is that clear? Other thing that they will also do to confuse you guys, they will write this as 4.18 kilojoule per kg per Kelvin. Both of these are same. Both of these are same. So they can confuse you doing a lot of different things. Okay, be very keen on the units. This is my advice to you guys. Okay, so whenever you're working, first thing is never work with kilojoule. That's my advice. Never work with kilojoule. Always convert to joule. Now you may choose to work with kg or gram depending on what the masses are. You may have grams given in the question. You may also have kg given in the question. Okay, based on that, do the calculation. If your mass over here is in kg, then your specific heat capacity, choose it in kg as well. Okay, so convert accordingly. Keep that in mind. Any question about that? Any confusion about the units? I don't know if my internet is bad. Sorry if it is. Okay, so hopefully you guys understand how the units work. Okay, don't get confused about the units. So now coming back over here, since everything is in terms of gram and joules, my life is a bit easier. Okay, my life is a bit easier. So I get to work with this simply. So now they've given you the specific heat capacity of water, they've given you the specific heat capacity of mercury. Here we have very important informations over here. Now they're telling you the glass of the thermometer and the beaker containing the water can be considered to have negligible heat capacity. What does that mean? Basically, we don't need to consider the glass and the beaker, the glass of the thermometer and the beaker in our equation. That is to say, if my liquid over here loses temperature, so liquid loses energy, and who gains the energy? Mercury. Mercury gains the energy. So the transfer of energy is only between the liquid and the mercury. The glass or the beaker, none of them are doing anything. We are not losing any energy to the glass or the beaker. Okay? The reason they say that is because often energy is lost in the surrounding. You've often heard this, right? So over here, you can just consider the energy transfer to be between the mercury and the liquid. Moving on with that idea, how do we form the equation? Now they're asking you calculate to three significant figures the final steady temperature indicated by the thermometer in the water. How do you work with this? It's simple. You have to equate how much energy has been lost to how much energy has been gained. Remember our kettle example right now, 5 minutes before? What did we do? We provided the energy by the kettle, so loss of energy by the kettle, and gain of energy by the beaker of water. So we equated both of those together to find the increase in temperature. Or, yeah, to find the increase in temperature. Over here, what we will find is the final steady temperature. That's the only difference. We still equate the gain and loss of energy. The only difference in this question is what is the final temperature? How do we formulate that equation? Let's look into this. So the beaker of water, what does it do? It loses energy to the mercury, right? Granted, you agree with me on that. I can say the energy transferred by the liquid is simply the mass of the liquid, which is 18.7 grams. So this is my M, and times the C, specific heat capacity of liquid, right? Times the change in temperature. What is the change in temperature over here? Doesn't the beaker lose energy? So if it loses energy, won't the temperature of the beaker decrease? Hypothetically, physics intuition, yes. If it's losing energy, obviously the temperature will decrease. So my final temperature is less than my initial temperature, which is what? 37.4. So what is the difference in temperature? 37.4 minus my final temperature, which is less than 37.4. So this ultimately is simply the del T. What is it? Del T, change in temperature, or del theta. You will see different symbols, different places. Phenomenal. Now, the gain in temperature. What is the energy gained by the mercury? What if the mass is of mercury, which is 6.94, whatever the specific heat capacity of the liquid is, which is 0.14. Notice over here, this is what I want you guys to notice. Isn't the specific heat capacity of mercury really less? Yes, it is. So it needs really less energy to gain its temperature. Okay? I want you guys to understand that. Okay? Now, what is the change in temperature over here? The final temperature of the mercury will be T, capital T. Same as this. But won't the final temperature of the mercury be larger than the initial temperature of mercury? It's gaining the energy, right? It's gaining the energy. Since it's gaining the energy, the final temperature of mercury is larger than the initial temperature of mercury. Clear? So this T, these two T's are the same. These are the final temperature, which is same in case of energy transferred and in case of energy gained. Okay? Whenever the temperature for the mercury and the water is the same, that is when we take the reading from the mercury. Now let's equate these two equations. Energy gained equals to energy transferred. What do we find? What do we find over here? This over here, this over here. And if you solve for T and make T the subject, do you know what you get? 37.2. Do you want me to do the calculation over here? Give me a thumbs down or a thumbs up. Do you want me to show how T is 37.2, or are you satisfied with the answer? I'm just telling you guys that temperature, if you calculate for T, yeah,
Sir, so is it like final minus initial or like the highest minus the lowest?
I have taken highest minus the lowest. The reason is I don't want there to be a negative sign in front.
Okay.
Okay, even if it is a negative sign in front, doesn't matter. You can just say that the final minus 37.4. If you write this is okay as well, because the negative sign in front of the expression won't affect because everything is multiplied. Yeah. Okay.
Oh,
Great. Great. So you can do final minus initial. The reason I did the bigger minus smaller is because I will get to work with positive numbers. So it's easier for me. That's it. Nothing else. So I will also advise that uh, that's better because you don't.
so for the one with the greater temperature, I can always just do um like initial minus final as well,
Yeah,
right?
you can. You
All
can.
right.
You can do that. That's not a problem. Yep. Okay. Okay. Fair enough. So are you sure about the answer now? Right? You're absolutely clear on how we get the temperature. If you just open the brackets, you multiply everything, what you will see is T comes out to be 37.2. Okay. By the way, for you saying that T would be in front, then you need to add a minus sign in front as well in that case. Okay. Otherwise, you will get a wrong answer. The reason you do that is since you're doing final minus initial on either side, you need to say that the gain of energy is positive and the loss of energy you have to express as negative in that case. Otherwise, your answer will be wrong. Okay. So if you're doing final and minus initial on either side, you need to have a positive or minus sign in front of the equation based on which one is transferred and which one is gained. Otherwise, your answer may be wrong. Okay. You can try it out, but I'm pretty sure the answer will be different because when you open the brackets, things get multiplied. Okay. So there's a sign distribution over here. And in these cases, answer can be wrong if you change the position of t over here. Okay, when I put t over here and t over here, I've already accounted for which one is transfer and which one is gain. So my sign is actually accurate over here. Now, if you just put t always as the final temperature, then you have to include a minus sign over here for which one is transferred and which one is gained. Do you understand, Owen?
Yes.
Okay, fair. So that is why I took what the way I put it over here. So, okay. Now, if you solve for T, you get temperature as 37.2. Now, my conversation again is notice, did the beaker with the liquid lose temperature? Yes. How much? Zero point 0.2 degrees Celsius. That is it. Even though the mass of my liquid and mass of the mercury is very similar, even then, the loss of temperature is what? 0 0.2 degrees Celsius. That is the power of specific heat capacity. That is why we use mercury thermometers. Okay, I hope the concept is clear. Any question about how we did this calculation? I hope not. I'll move on to the other question. What is this question saying? Very fast. Suggest one change that could be made to design of the thermometer that would enable it to give a more accurate measurement of temperature. What do you think? There are two suggestions I can bring over here. How to make sure that the temperature loss of the liquid is very little. One thing I can do is I can decrease the specific heat capacity of the liquid inside thermometer. So instead of mercury, I use a metal that has an even lower specific heat capacity. Or I can decrease the mass of mercury. These are the two things I can do. What happens if I decrease the mass of the mercury? Less energy is needed to raise the temperature of mercury. What happens if I decrease the specific heat capacity of the liquid? That is, I use something instead of mercury. Even then, less energy is required to increase the temperature of the liquid inside thermometer because the specific heat capacity is less. So, use a liquid with lower specific heat capacity or use a smaller mass of mercury. Okay? Here, these are the two things I can do. Now, explain why the thermometer in figure 2.1 does not provide a direct measurement of thermodynamic temperature. This is a very simple question, almost confusing for how simple it is. It's just that on the thermometer, they have given the calibration with respect to what? Degree Celsius. Okay, so if they've given the calibration with respect to degree Celsius, I now need to sit down and convert it to Kelvin scale and then get the reading. Okay. So it does not provide a direct measurement of the thermodynamic temperature. That is it. Why? So thermodynamic temperature is measured in Kelvin and 0 Kelvin can't be measured by this thermometer. Over here, what do we have? We have 0 degrees Celsius. That is not equivalent to 0 Kelvin. So the calibration is in Celsius scale. Okay, so that is why we cannot get a direct measurement of the thermodynamic temperature. Clear? Clear? Okay, fair enough. So that's the answer. Now, next one is thermodynamic temperature T Did someone say something? Okay. The thermodynamic temperature T may be determined by the behavior of a type of substance for which T is proportional to the product of pressure and volume. Did we discuss this last class? Do we remember PV is equals to nRT equation? Over here, PV is proportional to the thermodynamic temperature. Do we remember this? Yes? So for this equation, what is the assumption? That the gas is an ideal gas. So whenever you work with ideal gases, this equation is valid. And I will discuss this extensively in the ideal gas. This question you won't be able to answer, technically speaking. You guys may be, but technically speaking, you need to understand ideal gases, which we will discuss right now. So PV is equals to nRT is called the ideal gas equation. It's in the name, my friend. It's in the name. So PV is proportional. Product of pressure and volume is only proportional to the thermodynamic temperature if you're working with ideal gases. What is ideal gas? Ideal gas is when we consider that there is zero potential energy of gases, or there is zero intermolecular forces between the gas molecules. Is that clear? So the intermolecular forces between gas particles are very little or negligible or zero. It is only then that we can use this equation. Okay. Again, look at this thermodynamic temperature. Even when they ask you questions, they're going to make sure that they specifically write down thermodynamic temperature whenever they're going to work with these stuff. PV is equals to nRT. Did they mention thermodynamic temperature over here? No. See, the temperature is 37.4 degrees. Here they don't, because here Kelvin or Celsius isn't relevant. When you're working with ideal gases, yes, my friend, thermodynamic temperature, you need to specify. Okay? So I just wanted to show that. Next chapter. As mentioned, we will be covering ideal gases in this class as well. Any question on the temperature chapter, guys? Any question to this point? Are we on page with everything? Okay, great. So now, give me a minute, please. So this is the ideal gas. You can just write a few things down if you wish to. Okay. This is your 15, chapter 15. We have progressed quite a bit till now. Okay. Okay, so the first thing we are going to discuss when talking about ideal gases is different types of law. Different types of what? Different types of gas law. So we basically, what we do is when working with gases, we have found a few very interesting relationships when working with ideal gases. Okay. When working with ideal gases, what we found out was three things. There's a relationship between pressure and volume of gas, interestingly enough. There's a relation between volume and temperature of gas, interestingly enough. And there's also a relation between pressure and temperature, interestingly enough. So there are three relations we have found out. And these three relations are the fundamental of the ideal gas law. So where did the ideal gas law come from? PV is equals to nRT. This is the ideal gas law. Where did this come from? It came from three basic laws. Three basic laws: Boyle's law, Charles' law, and pressure law. If you understand these three relationships, you can combine these three relationships and write down the ideal gas law. Okay. Okay. So let's start off with the first one. The Boyle's law say that if the temperature is constant, pressure is inversely proportional to the volume. So if I have a box of any random gas, okay, any random gas, I have gas molecules inside, okay, and you know what I do? I take this box and I shrink this box. I shrink this box. What do you reckon is going to happen? What do you think is going to happen? I've decreased the volume. I've decreased the volume. What do you think happens? The amount of, or the N, the moles of gas, constant. No gas exited the box, no gas got into the box. You're working with the same amount of gas. Number of particles are the same. And if I decrease the size, our physics intuition says pressure increases. Pressure what? Increases. And we'll look into, through physics again, how we can prove this using equation, and which I find very interesting. Because what we take for granted can be proven by simple physics equations. Okay? So what does this relationship tell us? That if I shrink the volume with the same amount of molecules inside, the pressure increases. So if what does inverse relationship mean? If one decreases, the other increases. So if my volume is to shrink, my pressure is to increase. Do we understand that from this inverse law? Do we understand this from our physics intuition? Yes. Okay, great. Now look, an important part of this entire conversation is temperature should be constant. The reason I say that is if I increase the temperature, what happens? Pressure inside the box will increase even more kinetic energy, more collision inside, hence more pressure. What happens if I decrease the temperature while I'm shrinking the box? The pressure may just remain constant. Why? Because I'm decreasing the temperature, I'm decreasing the kinetic energy of the molecules. So the molecules stop colliding as much, stop applying a force on the walls as much. So what happens? Pressure can stay constant or even decrease, if I decrease the temperature enough. That is why in Boyle's law, they specifically mention temperature should remain constant for this law to be applicable. If you look at the PV is equals to nRT equation, for P to be proportional to inverse of volume, N, R, and T, all of them should be what? Constant. Be very clear on that. So temperature being constant is very important. How can I prove to you guys using maths, using the formulas, that if I decrease the volume, pressure must increase? Granted, temp is constant. Granted, the temperature is constant, and number of particles is also constant. Granted, these two are maintained. How can I prove to you guys that the pressure indeed increases inside the box? So the force inside any box or on the wall is simply defined by, for a particle colliding with a wall, they simply change in momentum, mv minus nv, that is change in momentum by time of collision. Do you guys relate to this? So for a single particle colliding with a wall, whatever the change in momentum it goes through, divided by the time of collision, is the force applied on the wall. Clear? Now, if I include n into the equation and say n is simply the number of collision. So if I have multiple particles And if I shrink the size of the box, what happens? There's little space, less space. So the number of collision increases. So if I increase the number of collision, what happens? Amount of force applied on the wall increases. And what do we know about pressure? Force per unit area. If my force increases, my pressure also increases. That is why if you decrease the volume with constant temperature and number of particles, pressure always increases. Great. Now, coming back to our PV is equals to
Sir,
nRT. Yeah,
could I take a
go ahead.
screenshot of that part just now?
Yeah.
Okay, thank you, sir.
Yeah. All right. So now the conversation is, how do I draw the graph between pressure and volume? The first one I want to show to you guys, if I say PV is equals to N, R, and T, and I say, well, P is simply equal to N, R, and T divided by volume, hence P is proportional to 1 by volume, while my nRT is the constant. So if I want to plot P versus inverse of volume, not volume, don't get confused. I'm not plotting volume on the x-axis. I'm plotting what? Inverse of volume. And what is the relation between pressure and inverse of volume? It's a linear relationship between these two expressions. So it's a straight line. And what is the gradient of this line? nRT. So it's basically y is equals to mx. What is x? 1 by volume. What is the gradient? nRT. Clear? Now, is this something that you're going to see in paper? Could, I don't know, I could just, if I was the examiner, I could make some very interesting question out of these. So you could come across some very interesting questions. It depends. And I'm telling you guys, thermodynamics in general will give you guys some of the hardest questions in the entire A-level physics syllabus that I've seen. I've done decades of paper, and again and again and again, it's always a thermodynamics topic question that just screws with the brain. Okay, so and I have some such question which I will eventually show you guys as well. So, and for that, the issue with the syllabus is the syllabus just goes till a certain amount of depth and just puts some question on the paper that requires so much more conceptual understanding that the students just don't prepare themselves with. So it becomes difficult. At least I have 2, 3 such questions where I wouldn't expect a normal student to understand it. So yes, now coming back to this topic, what do you have? You have a linear relation between pressure and inverse of volume. Okay, simple. What is the gradient? I told you guys, nRT. Now look, if I plot pressure and volume, what type of a curve it is? It is a y is equals to 1 by x curve. In a Desmos calculator, if you open up Desmos on your laptop or computer or phone, if you plot y is equals to 1 by x, this is the type of graph you see. And start playing around with the graphs, because it's always, if you guys are studying maths, physics, later on engineering, you need to understand how to work with graph. Okay, it's always better to understand how graphs work, how to make functions, how to change functions. It's a good skill to have. Doesn't matter what you do. I'm pretty sure if you end up doing STEM, you will have to work with multiple types of graph. Now, look at this. So when I have pressure versus volume graph, it is an inverse curve. Now, I want to ask you something. Every point, I'll change my marker. Every point on this graph, what do you think remains constant? What do you think remains constant in every part of, yeah?
The temperature.
Yes, yes. So over here, if I take this point and this point, So I can call this P1 and V1. I can call this P2 and V2. Both of these are equal. So P1 times V1 is equal to P2 times V2. Why? Because PV is equals to nRT. Did we keep the number of molecules constant? Yes. Is reaction of gas constant? This is 8.31. That is always a constant. It's just what we take. And is temperature constant? Yes. So PV throughout the graph, that is product of pressure and volume, is always constant. Granted, the temperature is constant, right? And the number of molecules are constant. So every point over here that you take, P times V is constant. So I can say this entire curve, whatever point you take, defines the same temperature. Let's say 298 Kelvin. Do we get that? Do we understand that? Yes. So every point on this graph describes the same temperature. Why? Because PV is equals to nRT. Okay. 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 Fair enough. Now, what is let's say I go from this point to this point. That is to say, I have some box over here, right? I have some box over here. And what I do is what the hell am I drawing? Just go on with my drawing. What did I do between these two boxes? I increased the volume of the box. Is that clear? What do you think happened? What do you think happened? The pressure decreased. It's an inverse relation between volume and pressure. As I increase the volume, the pressure does what? Decrease. Okay, fair enough. So now notice this. As I increase the volume, right, what happens to pressure? The pressure decreases. Accurate, right? And as my temperature remains constant, my pressure decreases. Yes, any question? Okay, so now what I want you guys to understand is as the volume has increased over here, as the volume has increased over here, what does that mean? The gas inside the box over here, the gas inside the box has done some work on the walls of the box to increase the volume. To do what? To increase the volume of the box. Hence, the gas inside the box or container did work on the container, on the box. So the work is done by gas over here. Work is done by what? By gas. Hence, the gas loses energy while doing the work. So if I have a box over here, right, I have gas molecules and they have high energy and high pressure, and I release the bearing of the box, what happens? The box now increases its size. Why? Because the gas inside now has pushed against the wall, and increased the volume of the box. Okay? So the gas did what? Work done. And how much work done? This area under the curve. Is that clear? Why? Did you guys study work done is equals to pressure times del V? So this equation doesn't apply over here because over here pressure needs to be constant. In our case, is pressure constant? No, pressure changes. But does volume increase? Yes, it does. Whenever the volume is increasing due to the gas inside, work is done. Work is indeed done. Okay? Whenever the volume increases or decreases, work is done either on the container, that is on the gas, or by the gas. And over here, since the volume is increasing, that is the gas inside the box is doing the work, the gas inside loses that energy to do that work on the box. Yeah,
Buster,
go ahead.
when
Yeah.
volume for volume to increase,
Yeah.
isn't it like when there's an increase in pressure, the
Yeah.
molecules or the particles are closer together, so there's more frequent collisions, right?
Yes. Yes.
So isn't that increasing volume? Like,
Depends what you're doing. If let's say you have a closed box, right? And let's say I have somehow decreased the volume of this box, I've shrink the box while keeping what? Temperature constant. While keeping the temperature constant, and I have decreased the size of the box. Okay. Now, yes, you're right. The pressure has increased inside the box. So look at this. If I decrease the volume, what happens? Pressure increases, right? So pressure has indeed increased over here.
yeah,
Or is it something else that you're asking?
yeah. I'm saying like when pressure increase and they since they're coming to a closer
Yes.
space,
Yes.
don't we say the volume increase or no?
No, I mean, if you're keeping the volume constant, depends what the situation is. If you're decreasing the volume, then the volume is decreasing. And if you have to keep one thing constant in your
How do
conversation,
you
which one are you
decrease the
keeping?
volume? Like that's what I'm wondering. How do we
Oh, how
decrease?
do you decrease the volume? Okay.
Yeah.
Have you seen this example? This is a piston. Okay. So I push in this piston inside, and this is a container.
Yeah.
Okay. So there are gas molecules inside, and there's a piston over here, and I push this piston inside. So does the volume decrease as I push in the piston?
Yes.
So this is how you decrease the volume. This is one way to do it,
Oh, all right.
right? So as you decrease the volume over here, does the pressure increase? Yes,
Yeah.
the pressure increases over here. And the one thing to make sure is temperature must be constant over here for this PV, P1 V1 is to P2 V2 ratio to be constant. That is for the graph to always look like this for a specific temperature, 298, let's say. Okay, clear?
Yes.
Okay, perfect. So now look, what does this shaded region say? This is the work done by the gas. Why? Because you guys know work done is pressure times volume. But over here, you can't use that equation, can you? Because pressure is not constant. How do you then find out the work done over here by the gas? Area under the curve. So you integrate, if this is V1 and this is V2, you integrate V2 and V1 of pressure. Okay, dV. So you integrate pressure from V1 to V2 to find out the work done by the gas. But do you guys need to do that? Nope. You guys don't have that in syllabus. You guys don't have to integrate curves to find the energy. So don't worry about it. Okay. But in general, you need this idea though, that the area under the curve of a pressure volume graph is what? The work done by the gas or on the gas. If the volume is decreasing, what do we say? Work is done on the gas. Work done on the gas. If volume is increasing, work done by the gas. Okay. Okay. Fair. Any question of this? Let me know. I've extensively covered the Boyle's law part. Now, Charles' law. Once I have set the tone with one of the law, it's easier to understand the rest. So PV is equals to nRT again. Charles' law says if the pressure is constant, so I'm keeping this constant, volume is proportional to temperature. So number of molecules and gas constant is constant as well. So I can say volume is proportional to temperature. Can I say that? Yes, my friend, I can say that. Okay, volume is proportional to temperature. What happens? Basically, again, the piston example, if I use that I was explaining before, right? So I have a piston over here, right? So if I decrease the volume over here, and I somehow maintain the pressure inside. Now you will ask me, how do I maintain the pressure inside? Well, in industry, they have multiple ways to do that. They may have a pipe over here, and they may have a valve over here, and which indicates the pressure inside. And as the pressure builds up inside the box, inside the piston, right? What they do is they release that pressure. So in industry, how it works is, or in labs, how it would work is there's a valve and they release the pressure to keep the pressure constant. Okay, that is how the pressure is kept constant. You guys, I'm pretty sure you'll be confused about how is the pressure kept constant in this system. So that is how practically it's done. I have never really worked with it. I can't give you lab experience. I've never really done. I've never even seen this experiment work out in real life. But yeah, I mean, I'm pretty sure someone somewhere has done this. But yeah, so point is for Charles' law to work, your volume, if increases, that means the temperature inside the box container has also increased. Why? So let's say if I have a box, logically, if I want to answer your question with physics intuition, where did the box go? Oh, you know what? I'll just use this. Okay. Right, this is the box I have. Fair? Now, if this is the box I have, and I have multiple particles inside, and number of particles don't really change, well, if the temperature increases, T increases, what also increases? Kinetic energy, my friend. If kinetic energy increases, velocity also increases of the particle. So more collision, right? More collision wants to take place. But number of collision, if increases, pressure also increases. Doesn't it? Doesn't it? We saw it over here. Over here. We saw number of collision increases, pressure increases. But I want to keep the pressure constant. I want to do what? Pressure constant. How do we do that? How do we do that?
By pressure, sir,
It's
do we mean the pressure like of the container or the molecules or
Yeah, we mean basically the pressure inside the container due to the molecules,
all right.
right? So inside, due to the molecules, the pressure on the wall of the container, right? That's the pressure, not the atmospheric pressure. No. Okay. So basically, if my where did it go? Okay, if my temperature is increasing, kinetic energy is increasing, velocity increasing, and number of collision is increasing, then the pressure will also want to increase. So how do I make sure that pressure is constant? I simply increase the volume. Okay, so that the pressure remains constant. I've increased the spacing. So even though they have increased temperature, now I have compensated for that by increasing the volume. That is the physics intuition, my friend, again. Okay. So I hope you understand how this is working. Okay? So I compensated for the frequency of collision by increasing the volume. Okay. What did it is over here? Oops. Okay. So that's how it works.
So
Eh,
sir,
Yep.
basically like as first when we increase the temperature, the kinetic energy of the particles increase, right? And
Yep.
so the number of collisions also increase. But
Yep.
since we want to keep it constant, we also
Yep.
increase the volume.
Yep.
Do we increase the volume or like when we increase the temperature, the volume also just increases? Is it like that or do we do both separately?
No. So here's the thing. Depending on, okay, so now it gets a bit more technical, how you're asking how the process happens. So if you have a box and basically I don't like working with the box idea, I go back to the piston idea because this is I guess in the industry this is how they would show the example. So now what you're asking is if I increase with heat, right? I provide some heat. What is this fire? Right? I provide some heat, I
Yeah.
increase the temperature, right? And pressure builds up. So what happens? You're telling me, does it naturally push out the piston and increase the volume? Well, it
Yeah.
will. Yes, it will. You're not wrong. It will naturally, if I just release the piston is released, it will move out. But you know what will happen? It will move out until the outside pressure, that is 1 atmospheric pressure, equals the inside pressure, that is 1 atmospheric pressure. So it will want to basically uh, make sure the pressure outside and the pressure inside is equal. Okay, so I can't just release the piston over here. No, I can't do that. I have to manually, or by whatever the system is, I have to make sure the piston only moves out so much that the inside pressure just remains constant. So if the inside pressure is 3 atmospheric pressure, I just want to move the piston out manually just so much that the 3 atmospheric pressure inside is maintained. What happens if I release the piston? If I completely release the piston, the 3 atmospheric pressure inside the piston, that was the initial condition, will drop to 1 atmospheric pressure. So no, we don't release the piston completely. We don't do that because then it will want to uh, maintain the same pressure inside as outside. Do we get the idea?
All right. So then how do we increase the volume then? Like,
So we basically control how much the volume is increasing. There's a mechanism of the piston. So we only pull out the piston or release the bearing only so much that the piston will only move out by certain distances to increase the volume by a certain amount such that the pressure inside remains constant. So there's a valve over here, there's a valve over here, and we monitor the valve. So we keep increasing the volume and see does the pressure remain constant. So there's a line over here that indicates the pressure. So we want to make sure this line doesn't go around, right? Doesn't increase.
all
Okay,
right.
so we keep making sure that the pressure inside remains constant. Do we get the idea?
Yeah. So the main thing about the frequency of collision is pressure.
Yes, yes, yes. So the frequency of collision increases, pressure also wants to increase, and we compensate for that by increasing the volume.
Okay.
Okay, great. So that's how it works. That's how volume and temperature is related. And I showed you guys how the volume wants to increase if the temperature increases, right? So it's simply what the particles want to do when temperature increase. The pressure wants to increase, and if the pressure wants to increase, if I just release the bearing, the volume will also increase. If I stop, you know, if I make sure that the walls of the container are flexible, what happens when you blow out a balloon, right? You try to build some pressure inside, right? But the balloon itself, based on its structural integrity, starts expanding. Till what point? Till the point that the pressure outside somewhat equals the pressure inside. Okay, that's how a balloon works. And often, if the structure of the balloon is strong enough, then we will blow in so much air that the pressure inside is actually more than the pressure outside. But if the balloon is weak, then if I blow in too much air inside and the pressure is too much inside, then the balloon will burst. That's why balloons burst. It's simple physics, right? That's how pressure works, right? That's how pressure works. Fair enough. It's the same logic everywhere. Same logic everywhere. You can use any of the law and justify what you see around yourself. Okay. So now, if volume is proportional to the thermodynamic temperature, I can say that the V1 by T1 is always constant. That is to say, V2 by T2 is also constant. Are we confused about this? If you are, I'll simply say PV is equals to nRT, right? So can I take temperature to the other side? Volume by temperature is simply nR by P. Sorry. Is this constant, my friend? Is this constant? Yes, it is constant. Hence, the ratio between volume and temperature just remains constant. That is all I'm showing over here. The ratio between volume and temperature remains constant. Okay, that is all I'm showing. So V1 by T1, if I increase the volume and I increase the temperature by the same proportion, the ratio remains constant. That is all I'm saying to you guys. Okay, give me a moment. Okay, so yes, the proportion of volume and temperature remains constant. Granted, pressure is constant. Granted, your pressure is constant, number of particles is constant, reaction gas constant is constant, which is always constant. Then the ratio of volume and temperature indeed remains constant and is equal to nR by P. If I draw a graph between my volume and temperature, what happens? What do we see? Try it out yourself. Okay, so I make volume on the y-axis, so nR by P, temperature. What is the gradient over here? Any guesses? What is the gradient over here between volume and temperature? Nope. No? No idea?
The gradient
The
will be
energy.
nr over p.
Yeah.
Yes, nR over P. Right. So the gradient will be nR over P. Correct. So the line that we have drawn over here, if this is my y, this is my x, this nR by P is simply our gradient. So the gradient of this line is nR by P. Great. So this is how we work with the graph. Now, this you may get confused about, you may also not get confused about. Let me explain. So look, will I draw on this? I'll just copy this. I don't want to ruin that. Okay, P and Boyle. P and Boyle. So what do we have over here? We have plotted pressure versus volume for multiple temperatures. Let me put in another temperature over here. Let me put in yet another temperature over here. What did we see before? Before. Okay. We saw that for temperature constant, let's call this 300 Kelvin. Let's call this 250. Let's call this, if you just stick with me, okay. What can I call this? 275. You know what? I will just call this 300. I'll call that 350. Okay, look at this. For temperature being constant on a PV diagram, what do we see? If temperature is constant, P times V is always constant. So P1, V1 and P2, V2 is always constant if I go through one of these curves. Over here, my temperature is constant. On this line, at every point on this line, the temperature is constant, which is 350 Kelvin. So my P1 times V1 is constant throughout. Okay, my pressure times volume on this line is constant throughout. What happens if I decrease the temperature? What happens is the graph shifts below. Why? Because the pressure times volume, the product of P1 and V1 has decreased. Has what? Decreased. Okay, has decreased. So when I decrease the temperature, the product P1 V1 decreases. Okay, that's why you see for lower temperature, the graphs keep shifting below the graph. Or I can say the opposite.
Sir, so like P1 V1 is equals to temperature.
P1 V1 is equals to nRT. And a component of that is temperature.
Oh, all right.
So all I'm saying is basically N and R never really
Yeah.
change.
So they are like proportional to each other. So if the value of that decreases, that means it's either lower temperatures like that.
Yeah, exactly. So when you're working with this, volume is proportional to the temperature. And this is what I want to show you guys. That first thing I want to clarify is how different temperatures on the same PV diagram looks like. So different temperatures basically look like these graphs. As the temperature increases, the graph shifts up. The curve shifts up because the product of P and V has increased. So over here, whatever P1 V1 is, the P1 V1 is same, right? Right? Oh, what have I written? So over here, over here, over here, over here. P1 V1, P2 V2, P3 V3 is same, right? It's the same. Okay, so it's constant throughout this curve. Now over here, let's say P4, V4, or P5, V5, so on and so forth. Over here, the product of volume through this curve is less than the product of pressure and volume through that curve. No matter what point you take, doesn't matter. Doesn't matter. Does not matter what point you take on the graph. The product of pressure and volume through this curve is the same, which is nRT, n times r times t. And the product of pressure and volume through this white curve or semi-green curve is also the same. But that product is simply less than 350 or less than 350 times nRT. Okay, over here, P times V is again less throughout the curve. Throughout the curve, P times V is constant, my friend. P times V is constant, but that constant has simply decreased as I decrease the temperature. Why? Because nRT. If I decrease the temperature, PV as a whole has decreased. Okay, that's the first thing I want to show you guys. The reason I've showed you guys is I want to talk about the Charles law extensively. Okay. Whoop. Now look, what does Charles law say? The Charles law says pressure should be constant, volume is proportional to temperature. Let's look. If I draw infinite lines over here for infinite temperatures, it would basically look like this, right? Infinite lines for infinite temperatures inside. Infinite temperature is in if I just fill up this curve with multiple other, 201, 202, 203, so on and so forth, then this entire graph would be filled. So considering that, let's say I want to keep well, pressure over here, P1 is 1 atmospheric pressure. And I want to analyze this point. So I'm going to keep the pressure constant at 1 atmospheric pressure. Just follow me over here. If I keep the pressure constant and I increase the volume, what do I see? Doesn't the temperature increase? First, I cut the 200 Kelvin graph, then I increase the volume and I'm cutting the 250 Kelvin graph, and then I'm cutting the 300 Kelvin graph, and then I'm cutting the 350 Kelvin graph. Okay. So as I increase the pressure, sorry. As I keep the pressure constant and increase the volume, the temperature is increasing. This is what I wanted to show you with this graph. Okay. As my volume increases with constant pressure, my temperature also increases. And this graph is simply the proof or a graphical proof of this relationship. That volume is proportional to temperature, granted pressure is constant. Do we get the idea? Now, these graphs, I am telling you, understanding this will be so important for you guys. Very important for you guys. I don't know what type of questions are going to come. So you need to understand this. Now, over here, what is the work done? If I say I kept the pressure constant at 1 atmospheric pressure and I moved from V1 to V2, what is the work done? Work done will be pressure times del V. What is the pressure? 1 atmospheric pressure times del V. What is del V? V2 minus V1. Okay. Okay. Over here, I can use this formula. Why? Pressure is constant. Pressure is constant over here. Is that clear? So I can use this formula to find out the work done by the gas. If the volume is increasing, work done is by the gas. If the volume is decreasing, work done is on the gas. Volume is
Sir,
decreasing, that means
in what case is this? Pressure is constant.
pressure is constant. So if I keep the pressure constant over here, right? I make sure the pressure is always 1 atmospheric pressure, and I keep increasing the volume as the temperature increases. Then how do I find out the work done by the gas, pressure times change in volume. That is the work done by the gas. Okay,
All right.
fair enough. And why can we use this over here? Because pressure is constant. Previous case, could we use it? No. Why? Pressure was not constant. We had to integrate the area under the curve to find out the work done by gas. And integration over here is not in your syllabus. So you don't have to worry about it. Okay. So that's pretty much it. Yeah, I've covered everything with that. And one last thing, if you allow me to show you guys, then I'll end this class. You guys do have quite a bit. Uh, Half of it is just extra stuff done by me. So you don't need to worry about it. I'll just show you guys what you guys need to know. Okay. Uh, Even though we have covered only this much, at the core of it, it's simply the big derivation, this one, two derivations, and Boltzmann constant derivation, and kinetic gas of theory. Okay, and the Avogadro's constant. Okay, so you have a bit left, quite a bit left. Next class, hopefully we can cover. But yeah, the graph part I do think is important to understand. You guys will, if I don't know if you guys have seen the past papers. If you look at the past papers, you will see the thermodynamic questions where they're asking you, they're giving you a graph and asking you to understand or show the energy changes through different points on the graph. Okay, so they'll tell you, okay, I keep the pressure constant, increase the volume, I kept the volume constant, increase the pressure, what are the energy changes? Okay, what is the final energy change of the entire cycle that the volume of gas went through, or the entire amount of gas went through? So for those questions, this part is a bit important, which is why I want to cover this extensively. Now, last one that I want to cover is pressure law. Okay, now for the pressure law, the idea is same thing repeated again. Over here, what are we keeping constant? Volume is kept constant. And we see that as the pressure increases, temperature also increases. You want the physics intuition of it? There you go. If I have a box, if I have a box over here, okay, I have a box over here, and let's say the volume is constant. Okay, I have no bearings in this box. It's solid box, and the volume inside is constant. What do? I heat this box up. What do you think is going to happen? The same thing we discussed in the last one. The particles gain a lot of energy, but now since the box is rigid, the number of collision due to the kinetic energy increasing, due to the velocity increasing, number of collision increases, and hence pressure increases. So the relation is as my temperature increases, pressure increases. Granted, volume is constant. Is that clear? Is that clear? Fair enough. As temperature increases, Ke increases, velocity increases, and if volume is constant, number of collision increases. As a result, force per unit area increases, hence pressure increases. What you have over here is, I would say, the gold standard of answering questions on paper. Reason I say that is it shows the entire trail of thought that led to proving pressure is proportional to temperature. You have to show them why, after every single point, it leads up to the final answer. This is how you answer questions. If they ask you, describe the pressure law, why is pressure related to temperature? This is a great way to answer the question. Now, I wrote in short forms, you should not. Okay? You should not answer in short form. In that case, it's not the gold standard, it's horrible. But in terms of logic, train of thought, this is what you should follow. Okay? So for your SEQ questions, you always want to show the train of thought. This happens, hence this happens, therefore this happens, thus this is the result. Okay, you want to show the train of thought, you want to show the logic, you want to show the equation, you want to show them step by step what's happening. That's how you answer. Okay. Now, same thing. If I now get back to my PV is equals to nRT, what is proportion? What am I keeping constant over here? Volume I'm keeping constant. So P is nR by V. T, what is the magnitude? Sorry, what is the gradient over here? nR by. Is that clear? nR by V is the gradient. So my P is on the y-axis, temperature on the x-axis. nR by V. Okay, fair enough. So this is how pressure and temperature is related, proportional. Now coming back to the PV diagram, why do I keep again? Why do we keep getting back to the PV diagram? You will see this a lot on your paper. So I'm getting you guys used to these type of graphs. That is the entire point of showing you guys the PV diagram again and again and again in each of the laws. Because when questions come to you, this is the format it comes to you. Okay, so look, what is happening in terms of pressure and volume when I'm working with the, what is this law called? Pressure law. There's another name for this. I forgot. It's not just pressure law. You will find another name for this as well. Pressure law. I don't remember it. I can just, you can just search it up. You'll find it. So look, in this case, I want to keep what constant? Volume constant. What am I increasing? Temperature I'm increasing or pressure I'm increasing. Look at this. If I keep my volume constant and I increase my pressure, what happens? Temperature also increases. Okay. So look, if I have multiple graphs over here, so I have T3, T4 inside. As I increase the volume, it cuts through T3, then it cuts through T4, then it cuts through T2. And over here, the way I've written, you know what, I'll make your life a bit easier, T3, T4. So T1 is smaller than T2, is smaller than T3, is smaller than T4. So as you increase the pressure, this graph also proves that temperature indeed increases. This is the graphical representation of it. Using the curves, using the PV diagram. And you'll keep hearing this PV diagram. Okay. So this is how we can say, all right, as my pressure increases at a constant volume, my temperature also increases. Do you think there's any work done over here by the gas or on the gas? No. Does volume change? No. Will will there be a work done on or by the gas? Nope. Simple.
But isn't
No
the
volume change.
area increasing? Like
Area off.
like the so say PV gives the area under the graph since
Yes.
we're
So the
going
area under
straight
the graph.
upwards.
Yeah. So you're saying this part.
Yeah.
Yeah, no, that doesn't count. That is area under the volume curve. So that is basically, if you're describing this graph, it
Yeah.
means pretty much nothing because volume is not changing. Volume needs to change for your work done. Okay. Here pressure
Oh.
is changing for sure, but you're basically shading this area. When
So
you're
work
shading,
done depends on volume.
yes, 100% of the times. If there's no change in volume, no change in work done. That is a code to, I will go through that as well, thermodynamics chapter. Whenever there's a change in volume, it is only then there's a work done. That's the definition of work done. That's how we've set the definition of work done. Now, last thing, this is your proportionality between P and T. This is your proportionality between P and volume. That is pressure and volume. Let's combine these. If I say pressure is proportional to temperature and it is proportional to 1 by V, can I say pressure is proportional to T by V? Yes, that's how proportionalities work. Okay. So Pressure is, if I combine these proportionalities, pressure is proportional to T by V. Clear? Now, if I want to remove this proportionality, I have to say, well. Whenever you want to remove the proportionality, you have to include constant. And look, if I bring everything on one side, PV by T is proportional to 1. The moment I remove this proportionality, I say PV is equals to T, sorry, by T is equals to a constant. What is this constant? This constant is simply NR. So the ideal gas law is figured out experimentally using this. So we found out 3 proportionalities, joined them together, and saw that, all right, my PV by T is always constant. If you're working with the same number of particles in a box, let's say, no matter what you do to the particles over here, you increase temperature, you decrease pressure, you increase volume, the rest of the variables will compensate in such a way that PV by T always remains constant. What do I mean by that? If I change the temperature, the pressure and volume will compensate in such a way that PV by T remains constant. So let's say I have a box and the volume is constant over here. If I increase the temperature, the pressure will also increase. And that compensates for the increase in temperature over here. And PV by T remains constant as it is. You want to see an example of that? Let's see. If my pressure is simply 2 and temperature is 4, whatever it is, and volume, let's say, I keep constant because it's a rigid box, and I say this is constant. What happens if I increase the temperature from 4 to, let's say, 8? So if I increase the temperature to 8, you know how the pressure will react? Granted, the volume is constant. The pressure will become 4. And the volume will remain as 10 because it's a rigid box. And isn't this constant though? 2 by 4 is half. So 10 by 2 is 5. Over here, 4 by 8 is half. So 10 by 2 is 5. Do you see what I mean? PV by T, no matter what you do, whenever you're working with ideal gases, remains constant. Granted, the number of particles inside is constant. This is, again, the physics intuition. I have the proof by formula. But intuitively speaking, this is how it makes sense. If you want to understand how it makes sense, this is how it makes sense. That PV by T is always constant. Okay, any confusion till this point? We have completed one big chapter of ideal gas, arguably one of the most important chapters. Okay, any question till this point? I have taken 14 minutes over the allocated time. Sorry for that. But yeah, next class we move on with the rest of the. Any question?
No, sir.
Okay, great. So I will end the class today over here. Thank you for attending. If you have any question, you can ask me. Otherwise, you're welcome to leave for today. Thank you guys. Hope you guys have a great weekend.
Sir, do we have class tomorrow?
Yes, tomorrow you do.
All
Same
right,
time.
thank you.
You're most welcome. All right, guys, I'll end the class for today. Hopefully, no question. All right. Bye-bye, everyone.